Hi folks, let's talk about the general process where we go through when we are finding an instantaneous velocity from an xt, well, graph or function, let's call it. And let's say that there's a function that looks like this. What people typically say is, well, you find the slope of a tangent, but a tangent, people say a tangent is a line that touches a curve in one place. Problem is, you can't define a line with one point. So really, what we're really doing is, if you zoom way in on this, what we say, or what it looks like, is here's that function, and our quote-unquote tangent really, well, if we're finding a velocity, what we actually need is for the line to cross, oh, that's pretty good, is to actually cross the function, so therefore it touches in two places, making this actually a secant, where this secant defines a delta t and a delta x. All right? And maybe actually what we do is we zoom in on that part, and we do this process again where we draw maybe a different secant that touches in two places, where the delta t is really small and the delta x is really small. And eventually what we get to is, well, we get that delta x over some macroscopic delta t turns into what we call dx dt. Where, by definition, this is equal to the limit as delta t approaches 0 of that delta x over delta t. So what we're saying is we keep zooming in and zooming in and zooming in until we define this secant with a smaller and smaller and smaller delta t that encompasses a smaller and smaller and smaller delta x. And eventually we just keep shrinking it down until that delta t actually approaches 0. Right? And if we say back here that this curve is x as a function of time, well, it means that this value, we could say this is, if this is what we call time t, that's the value of the function at time t. And then we would say that this time is t plus delta t, and then this value of x is x at that time t plus delta t. And so our delta x then becomes, well, we say this is equal to the limit as delta t approaches 0 of, well, delta x, x at t plus delta t, that's our x final, minus x at t, that's our x initial, over the delta t. And this is really the definition of the derivative of a function. Another word to say the derivative is the instantaneous rate of change. All right, so let's do this with a couple of sample functions. Let's say that here's an expression for position as a function of time. All right, and so if we want to go through this process, well, the first thing I do is say, let's evaluate the function at that instant. So what you do is you say, well, the t that I put in is t plus delta t. Right? At what time? Well, at this time. So where you see a t, you put in that time. And so algebraically, right, we FOIL this, right, the first outer inner last, and I'm going to distribute the 5 at the same time, so you get this, 5t squared plus 10t delta t plus 5 delta t squared. Now, that's not anything magical, that's just algebra. FOIL and distribute. Okay? Right, and then our plain old, remember, our plain old x at t is 5t squared. So when we do, well, our delta x, which is x at t plus delta t minus x, minus x at t, well, we do this minus this. And those common 5t squared terms subtract away, and what we get is 10t delta t plus 5 delta t squared. Right? But if we're going through our process here, we want to take this and divide by delta t, divide by delta t. So what happens is a factor of delta t comes out of both of those terms. Remember, what we're doing here is come here, you. Yep, this comes here. Let's get rid of this. And this comes here, and those divided out, and that's there. Fine. Right. What we're doing here is actually finding, right, dx dt, the derivative of x with respect to t, which by definition is the limit as delta t approaches 0 of all this stuff. So we have dx dt, which by the way is the slope of the tangent of, it's the limit, yep, as delta t approaches 0 of what I have left, 10t plus 5 delta t. Well, as delta t approaches 0, it doesn't do anything to that, but it takes this and makes it approach 5 times 0. And what that says is if x is 5t squared, dx dt is 10t. Now this, you may notice, sort of looks like x. Now, I forget to do this. I should really write x as a function of time. This looks a lot like that, right? And it would be true if v naught is 0 and if a equals 10. Parentheses. Now, by definition, the instantaneous rate of change of position is v instantaneous. Or it's really v as a function of time. Well, gee, doesn't this look kind of like velocity as a function of time can be v naught plus at? But look, yeah, we said before that if v naught is 0, oh, look, and if a equals 10. Huh. So the kinematics equations show, the ones that we've been using, work with the idea that the velocity as a function of time is the derivative of position as a function of time. Velocity as a function of time is the instantaneous rate of change of position as a function of time. We can do it with the entire kinematics equation if we want, right? We can say if that's x of t, then dx dt is by definition the limit as delta t approaches 0 of x final minus x initial over delta t. So I say that x final is, well, I use this function, but every time I see a t, I put in that t. So that's v naught t plus delta t plus 1/2 a t plus delta t quantity squared. And that's v naught t plus v naught delta t plus, I'm going to FOIL and distribute at the same time, 1/2 a t squared plus the inner outer gives me 2t delta t, but times that gives me just a t delta t plus 1/2 a delta t squared. X at t is just the v naught t plus 1/2 a t squared. So when I subtract x final, well, when I subtract x initial from x final, what I end up with is, well, let's see, this goes with that, this goes with that, and what I'm left with are those. V naught delta t plus a t delta t plus 1/2 a, whoops, that's a delta t squared. But if I want to take the derivative, I have to take the limit as delta t approaches 0 of that quantity divided by delta t. So dx dt is the limit as t delta t approaches 0 of v naught t plus a t delta t plus 1/2 a delta t squared divided by delta t. That's this. And okay, if we're dividing by a factor of delta t, I just realized that this is supposed to be a delta t right here. Am I right, people? Delta t. Right, there is a delta right there. Okay, so our delta t comes out of here, out of here, out of here. And we have that dx dt is the limit as delta t approaches 0 of v naught plus at plus 1/2 a delta t. Well, as delta t approaches 0, this term approaches 0, and, well, v as a function of time, which is the derivative of position with a function, or with respect to time, equals v naught plus at. No kidding, it does. So your kinematics equations have been employing, or at least agreeing with, what differential calculus says all the time, whether or not you knew it, which is pretty neat. You will try this one. You will do this one. You will prove, or you will calculate what the derivative of this function with respect to time is. Now what I want to show you is what we said is, well, if x as a function of t, well, actually we should write it like this, plus v naught t plus 1/2 at squared. Well, we're actually sort of saying that's a t to the first, and there's actually a t to the 0 there. And we have both sort of known for a while, but now have justified with our differential calculus that vt is, or v as a function of t, I should say, is v naught plus a t. Well, here's actually what's true. This is actually 0 x naught times t to the something, but kind of who cares, don't worry about that. And this is really, well, times t to the 0, and you could put a 1 there. And this is really kind of like there's a t1, t to the first there, and there's actually, we could say there's a 2 times a 1/2 there. So what's happening is, right, the algorithm, which is to say the series of steps that you follow when you want to take a function's derivative, is you can take the exponent, that the variable that you want to take the derivative with respect to, take the exponent that's raised to and multiply it by that term that it's in. Well, hang on. Yeah, right. So we take this exponent and multiply it by this term, and then knock that exponent down by 1. You could actually make this a -1, but it doesn't matter because it's multiplied by 0, so it doesn't matter what this exponent is. Right? Look, we took the exponent and multiplied it by the whole term, and then we knocked that exponent down by 1. So if we say that x as a function of t is some, I use a c, no, I use a d, c times t raised to the n, then the derivative of x with respect to t, which in this case is the instantaneous velocity, or velocity as a function of time. The algorithm says we do this: n times c to the t and to the n minus 1. Right? So you know that using the algorithm that this, well, if x of t is dt cubed, then v as a function of time, which is equal to the derivative of position with respect to time, well, the algorithm says you go 3 dt squared. So when you go through this exhaustive process of saying, justifying that, well, dx dt by definition is the limit as delta t approaches 0 of x at time t plus delta t minus x at time t, all divided by delta t, you will, when you do it right, come up with that expression. So this is no longer, you know, a practical way of solving the function. Solving the function is not the right word. A practical way of finding a function's derivative. There's nothing wrong with it. It's cumbersome when we have developed, you know, when we can agree that this algorithm works pretty darn well in lots of cases. Not all, but in lots of cases. Okay? Okay, that's it, people. See you soon.